All right, today we're going to start chapter 3, which deals with acceleration and motion. Now, in the last chapter, we looked at just motion as though it were a constant velocity or average velocities. But I didn't mention that there are very few times where there is just a constant motion. There's going to be some sort of change. When you get on the interstate, you accelerate in order to pick up speed. When you come to a stop sign, hopefully you slow down and come to a stop. So we're going to be looking at this chapter on dealing with acceleration. Motion can be either linear or nonlinear. In the previous lessons, we've just dealt with linear motion. We're also going to start dealing with some nonlinear motion now. And take, for instance, if I were in the classroom, I would take a ball and I would throw it toward an individual, just tossing it up in the air, and they would catch it. But if we look at that motion, it is not a straight line. It is going to be up and come back down. So it's just a nice little lob to a person. And we can see that that motion is not linear. It has some sort of angle to it. The question is, why is there that angle there? And the reason for that is because of a changing velocity. So constant velocity is very seldom felt. For instance, if you're in a car, maybe somebody else is driving and you lean your seat back, maybe you're on a trip or something, and you go to sleep. When you wake up, you may not even think that you're moving because you're going at a constant acceleration. Uh, we just took a trip on the way home. My daughter was driving. I was in the back seat. My wife was in the front, and I was taking a little nap. And occasionally I would feel the car move erratically. It didn't quite have the smoothness of changing lanes yet, and so it tended to be a very quick, maybe even jerky motion. Well, we can feel that because there's a change in my velocity, there's a change in an acceleration. So we feel those changes in acceleration, we feel those changes in velocity. So how can you tell if an object is accelerating? So up on your screen, I have 4 pictures, A, B, C, and D. And I'll give you a moment for you to kind of, in your own mind, describe what's happening in each of those 4 pictures. So we'll begin with A. If you look at A, there is a velocity of 0. The individual is staying in the same position. So there's no acceleration, and there's no velocity either. If we look at diagram B, we see that the individual is basically running at a constant speed, a constant pace. So there's no acceleration there, it's a constant velocity. In C, we see that there is more space between the last 2 pictures than there are between the first 2 pictures. And so there's an increase of space in each of the time-lapse photos, and therefore we can conclude that the object is accelerating. And then in the last image, we see that there is a deceleration because the images are getting closer and closer together. Now in the last chapter, we looked at position time graphs. In this chapter, we're going to look at velocity time graphs. And when you're working with these, you want to really make sure which one you're working with, because if you think that you're doing one and you're actually given the other, it's going to throw a lot of your numbers way off. So with velocity time graphs, as you would imagine, we're going to graph the time on the x-axis and the velocity of the object on our y-axis. And when we do that, we get acceleration. Acceleration is simply the change in velocity over time. So if acceleration is constant, the velocity is constantly changing in what we would consider a linear way. So if you look at this table here, table 3.1, and then the graph that coincides with it, you will notice that our line is a straight line. We have a slope that is constant. And since this is a velocity time graph, that means our velocity is constantly changing at the same rate. Very few times will this actually occur in real life because you're going to have things like wind resistance, you're going to have things like a car that is going to be able to accelerate at lower speeds faster than it is going to be able to accelerate at upper speeds. but this does give us an idea of what is occurring. If you figure out the slope, in doing so, you have figured out the acceleration. In this particular case, we have 5 meters per second squared, which means for every second that passes, our vehicle is increasing its speed by 5 meters per second. So when the time is 0, it's stationary. After 1 second, it's traveling at a speed of 5 meters per second. After 2 seconds, it's now 10 meters per second faster than what it was a second before. So it's now traveling at 10 meters per second, and so on. Keep in mind that this is not a distance. As you increase speed, you're going to increase the distance as well. And we'll talk about that a little bit later on in the year. Acceleration is going to be equal to the slope of the line. And that brings us to the concept of average versus instantaneous acceleration. Average acceleration is the change in velocity during some sort of time interval, maybe from start to finish. And it's going to be measured in meters per second squared. Instantaneous acceleration is the change in velocity at an instant of time. Now, this one's a little bit more difficult to comprehend because, as we mentioned before, an instant has a time of 0. So I can't take my change in velocity and divide by time because my time is 0. So instead, what we have to do is graph our velocity time. We would pick a point on the graph that we want to find the instantaneous acceleration. And then we would draw a line that is tangent to that point. And the slope of that tangent line is going to give us our instantaneous acceleration. Now, the way we display acceleration on a motion diagram is much easier. So, for instance, we want to show the average velocity of each time period. In this diagram, we have A. You'll notice that our velocity is increasing in each moment, which means we have some sort of acceleration. We see that by the differences in the changes of the lengths of our vectors, or the distance between our points. So to show the average acceleration, we simply subtract the velocity vectors from the one that follows it. So for instance, if I take that VF vector and I subtract the VI. Now in subtracting a vector, remember you're going to flip the vector around, and so you're adding a negative in a sense. And so when you do that, you get the change in velocity. Now if that change in velocity is over, let's say 1 second of time, then that's going to give you the average acceleration during that time interval. So let's work out an example problem. How would you describe the sprinter's velocity and acceleration as shown on this particular graph? From the graph, note that the sprinter's velocity starts at 0, increases very rapidly the first few seconds, but then kind of tapers off around 10 meters per second. Well, if we wanted to find our instantaneous velocity at any one particular moment, what we would need to do is draw a tangent line at that point. So if we wanted to see what his velocity or his acceleration was at 1 second and then at 5 seconds, well, at 1 second, we would put a tangent line and we would see that the rise over the run is roughly 3.4 meters per second squared. So at 1 second, he is averaging his acceleration at 3.4 meters per second. However, as he gets close to his peak, and 5 seconds later, he is only traveling at an acceleration of 0.030 meters per second squared. And this is a very common occurrence that would be seen in nature. Again, seldom do we see an average acceleration and an instantaneous acceleration being the same. For our purposes, for most of our book, we are going to be using the average accelerations, or we are going to assume that there is a constant acceleration throughout the entire thing.